All right, we'll just get started shortly, just waiting for a few more, and then we'll get rolling. We got a jam-packed meetup today, 2 talks. So stay tuned. We'll start shortly. I promise next time we'll have some waiting music so it's not so silent for everyone.
I can volunteer my dog to sing next time. She's busy at the front window of my house wooing at something outside, so maybe she could be the wait music.
Greatest hits from including Woo 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 and Woo Woo Woo. All right, I think we're ready to get started. Shall we get going?
Yeah, let's do this.
All right. Hello, everyone. Thanks for coming to the March 2021 Kubernetes and Cloud Native Eastern Canada Meetup. I got a jam-packed session for you today. As usual, we'll do our housekeeping, any news and notices from the CNCF as well as from our Eastern Canada team. And then we have 2 talks today, one from Rafal, architectural caching patterns for Kubernetes, and one from Pete, Knative tooling and observability. As usual, we have some prizes at the end. Johan has linked a survey in the chat, so if you could fill that out as we go, you'll be entered into that draw. So keep that open. So my name is Jason Hattie. I'm on the organization panel, and today from the panel from team, we'll also see Alex, Sebastien, and Johan. As always, thank you to our sponsors. Without our sponsors, a lot of this wouldn't be possible. So thank you to Red Hat, Elastic, D2IQ, StackRox, JFrog, Container Solutions, and AWS. If your company or a company that's interested in becoming a sponsor, just scan that QR code. It'll detail a little bit more information about what it means to be a sponsor and how they can be a sponsor. So just keep that in mind if you or your company is interested in becoming a sponsor of our meetup. So again, today's speakers, the CNCF Cube Canada and team will do some updates. We'll do that first. And then following that, we'll have Rafal do his talk about architectural caching patterns, and Pete, again, with Knative. All right, passing on for some housekeeping.
Yep, thanks, Jason. Next slide, please. So, of course, we're a global community across the eastern part of Canada mostly, but you can reach us, find us on multiple platforms, not only during meetups. So we're on LinkedIn, Twitter, and obviously our Slack channel, which is pretty active. So if you're not already a member of these, please join us. Next slide, please. Yep, we are open, of course, to hosting you as a speaker for any of our upcoming events, whether they will be virtual or even in person, maybe by the end of the year. We have 2 CFP links open. Yeah. You can submit to either one, and we will triage them. but keep in mind that local speakers are always preferred and will always be given a chance to speak at our events, even if we appreciate having world-renowned speakers such as Rafal with us today. Next slide, please. A few announcements. Next slide. Of course, we are mostly located across the eastern part of Canada, and last month we joined forces with the Halifax community, with Johan with us today, who will be helping us with Q&A towards the end of the talks. So we're very happy to broaden the scope of our membership. Thanks. Next slide. And of course, if you're all here today, it's because you've been gracious enough to RSVP to our event on the Cloud Native Canada chapter of the CNCF Meetup groups. This is a way for us to try and make things better as we organize virtual events that regroup members from all of our different cities. So this chapter is, for the foreseeable future, the location where we will post our events, as we want to make it easier for you to join and find links and not have to register to multiple cities, and reduce the confusion that we have. All right, that's it, I think. And we have CNCF announcements with Sebastian.
Yeah, hello. So the first big announcement today is the KubeCon and Knative Europe, which is taking place later in May. Registration is open. I think early bird is already gone by now, I guess. So you can go and check for their schedule. A lot of very great talks around Kubernetes and everything around it. There is a lot of co-located events. So to say a few of them, like Service Mesh, Prometheus related things, there are usually kind of training days also. So it's a very big event. So go there and check, please. Next slide is the US KubeCon. So it's already scheduled for October. It's supposedly to be in person. Hopefully, at least maybe a few of us will be able to attend that in Los Angeles. So great event. I put here the link to the calls, the paper calls. So if you want to talk to the KubeCon US, you can still register there and propose something. So schedule is not already settled, but yeah, it should come in the coming month. Then we have different CNCF projects that were updated in the last month. So Flux is one of them, Flux and Flux V2. So Flux is so it's a tool for keeping Kubernetes cluster in sync with your source of configuration. So we can think of GitOps here, and automate updates to configuration when there is a new code to deploy. And so there is a new version too. So it's not new actually, but it's like trying to get Flux V2 GA, so to fully replace the V1, and which support multi-tenancy and for syncing arbitrary number of Git repositories. That was a limitation of Flux V1, but they are getting past that. So next slide. Another tool that went, it's not new again, but it's the technology radar built by CNCF to track the technology usage. So the last radar was about secret management. And what we see here in the, to make it short, is HashiCorp Vault being widely used as a primary secret management tool. And like a lot of other tools like AWS Secrets and Cert Manager, which is more for a certificate, but still appear here. So check as often as possible here, as there are new radar focus every maybe like multiple times a year, I would say. Next slide is about Helm. So Helm had its a new security update, security audit made, which led to a new Helm 3.32 release following the audit. And so yeah, please upgrade. That's the news for Helm 2, or actually Helm 2, which is Helm 3. And then we have Falco, which is runtime security. So deploy that and ensure that everything you're doing in your Kubernetes cluster is as you think it is. And so it's promoted by SysDig, which also work on eBPF props and things like that. And so the core component of Falco are now part of CNCF. So that makes it like a reliable tool for Kubernetes.
All right. Thank you, Sébastien. And we are now on to our first talk with Rafal. Rafal is a cloud native team lead at Hazelcast, and he is the author of the book Continuous Delivery with Docker and Jenkins. He's a trainer, conference speaker, and he specializes in Java development, cloud environments, and continuous delivery. He is a former employee at a number of companies and scientific organizations, including Google and CERN. Rafal, take it away.
Hello, everyone. It's a pleasure to be here. Thanks for the introduction. And let me screen share and go straight into my talk. So my talk is titled Architectural Caching Patterns for Kubernetes, when I will talk about different topologies that you can use, how you can deploy basically caching layer in your application for your application at Kubernetes. I normally tell a few words about myself, but you already introduced me, so it's exactly what you said. A few words about Hazelcast, where I work. So Hazelcast is a distributed company. We are an open source company, so we produce open source software. We have free products, which is Hazelcast IMDG, which stands for In-Memory Data Grid. It is basically used for caching, for any distributed computing, and we call it a Swiss knife for any distributed operations. Second product is Hazelcast Jet, which is a library for stream processing. And the third one is Hazelcast Cloud, which is basically Hazelcast put as a service. So our agenda for this talk is pretty simple. There will be a short introduction about caching in the microservice world in general, and then we will walk through all possible caching topologies, patterns that you can use in your system deployed at Kubernetes. While I'll be talking, I would like you to think about two things. So one thing is which of this pattern you use in your system, because this list is complete, and so you must use one of this pattern, and you most probably use caching somewhere. And the second thing is, would it make sense for your system to change to any other pattern? Would it be beneficial for your architecture of your system or for any other reasons? And with these questions, I go straight into the introduction. So we are in this microservice world deployed at Kubernetes, which usually looks something like that. We have a lot of services. The services, they have different versions. They are written in different programming languages and they use each other. And now the question for this talk is, on this diagram, where is the right place to put your caching layer? Is it inside of each service? Or maybe we should put it outside as a separate unit, as a separate thing in our system. Or maybe we should put caching in front of each service. And that is what this talk will be about. So first caching pattern, first way how you can deploy your cache is embedded cache. So embedded cache basically means that you use a caching library inside your application. So the flow is as follows. Request goes to our system, it goes to the Kubernetes service. Kubernetes service load balances the traffic to one of the Kubernetes pods. And then inside the pod, we have the application. And inside the application, we use cache simply as a library. And application checks, okay, have I already executed such a request? If yes, just return the cache value. If no, do some business processing, put the value into the cache, and return the response. So the idea here is very simple. It's so simple that you can even implement it on your own. If you happen to use Java, that is probably how you could approach it. If you use other languages, it will be very similar. So we can use a collection. In Java, it would probably be the concurrent hash map, which we use as a cache. So request goes to our system. We check, okay, if cache contains this request, if yes, return it from the cache. If no, do some processing, put the value into the cache, return the response. As simple as that. So you can implement it on your own using standard language collections, but you better not do it. Why not do it with standard collections? Because collections in any language, they are not good as a cache. They are not good as a cache because they have no eviction policies, no max size limit, no statistics, no expiration time, no notification mechanism. So they lack a lot of useful caching features. That is why you are better off using some caching library. If we stick to Java, for Java, Guava is a very good library for caching, or EHCache. If you don't use Java, again, for any language, you will use a very good caching library. No problem with that. Now we can move this idea of caching one level higher and put it into our application layer. So for Java, still the most popular is Spring. So in Spring, if we would like to cache something, we don't need to write on all this boilerplate code. We just say, let this method be cacheable. We annotate it, and now every call to this method will first check if the given ISBN is found in the cache called books. If found, return the cached value. Only if we cannot find the value in the cache called books, we execute a method find book in slow source. However, be careful, because Spring, for some reason, they use concurrent hash map by default. So you'd better, first thing you do, you change your caching manager to some cache like Guava or any other caching. Coming back to this diagram. So far so good. Embedded caching is very good and simple, but there is one problem on this diagram. Think about it, like a request goes to our system, it's load balanced to the application on the top. We execute some business logic, put the value into the cache, return the response, everything is good. However, now the same request can go to the application, can be forwarded, load balanced to the application at the bottom. Because like Kubernetes service, it uses round robin, so it can go to any application. So now it goes to the application on the bottom, the same request, and we need to do this business logic once again, because this caches They are completely separate. They don't know about each other. That is why one of the improvements to the embedded cache would be to use embedded distributed cache. So it's still the same idea, it's still the same pattern, but this time we'll use a different library. So for Java, we can use Hazelcast, which is a distributed caching library. So how it looks like now. So now request goes to our system, it's forwarded to the application. And now no matter which application uses cache, it doesn't matter because both caches, they form one consistent caching cluster. So no matter to which cache instance we add the value, it's the same. So how it looks like in practice, if you'd like to configure this, what do you need to change? So if we stick to the Spring example, so for Spring, it's enough. Okay, I changed my cache manager to use Hazelcast. That's it. Everywhere in your application now, if you use cacheable, it will use Hazelcast as a caching layer. Now you may wonder, like, but how each cache instance know about each other? I mean, how they discover themselves. So we thought how to make it convenient for the users, and we came up with the idea of discovery plugins. So we actually have the discovery plugins for all used environments. And for Kubernetes, we have Kubernetes plugin. So in Kubernetes, these plugins are automatically detected. So Hazelcast running on Kubernetes will automatically detect, okay, I'm running Kubernetes, so I should use Kubernetes API to discover my fellow Hazelcast members and form one caching cluster. So you don't really need to do anything as a user. You just start your application and they will find themselves. Now, if you're interested in details, we publish a lot of blog posts how to configure this, or you can read the documentation, or just Google it how to set it up. But it's very simple. So that's how we ended up with this diagram about embedded distributed caching. So a short summary about embedded and embedded distributed caching, what it means to you. So from the good sides, configuration is very simple because the caching layer, it goes together with application. So you don't need to, to ask your ops team to set up anything for you, because it's already, you provide your application and the cache is already there. You have very low latency data access because cache is inside your application. You cannot do really anything better. From the downsides, the management of the cache is not flexible, because if you'd like to scale up your caching cluster, then you can do it only with your application. It's limited to your JVM or your language of choice, because you embed it inside your application. And the data is collocated with the application, which can be a problem or does not need to be a problem. Usually what we see for big enterprises, they don't want their data to be stored together with the application. So we covered embedded caching pattern. The next one is client server. So client server is kind of good old database style. So we use cache as a kind of database, which means that we deploy it separately. In Kubernetes, it will usually mean that you deploy your cache server as a stateful set, as a separate thing in your Kubernetes cluster. And how it looks like. So the flow is similar. Request goes to Kubernetes service. It's load balanced to one of the Kubernetes pod when application is running. Application uses cache client to connect to the cache server, which is deployed and managed separately. Now, if we compare this client server with the embedded solution, there are two main differences. So the first difference is this cache server. So before we didn't have it, now we have it. We need to manage this, so we need some ops effort. But from the benefits, we can manage it separately. So if all of a sudden you had free nodes of cache, you suddenly have a peak load, you need to scale it up, no problem, you can do it separately. Now, there is also a second difference if you compare it to the embedded mode. And the second difference is here. So the second difference is that now your application uses cache client, which connects to the cache server with some well-defined protocol. And that means that your application can be written in a different programming language than your cache server. And that is usually a very common scenario, that you deploy your cache servers and use different applications to connect to your caching servers. It is such a common topology that like Redis, Memcache, they are just prepared for a client server. They are not prepared for embedding them. How to set it up? If we stick to Hazelcast as an example, how you would like to set up client server in your Kubernetes cluster, how to do it? So you need to start caching server. With Hazelcast, you can do it with the Helm chart. You can also do it with the operator, really up to you. But it's as simple actually as running one command. Now, what about the client? So again, let's stick to the Java example, but obviously there are clients in many languages. But if we stick to the Spring example, what do we need to configure? Okay, I would like to use client. Let's use Kubernetes. Let's enable Kubernetes config. And then client will use Kubernetes plugin to discover Kubernetes server. So that's actually what you see. It's all you need to configure. And client will find its way to the server. So this is basically like our diagram. We have this separate thing, the server, and we have our application. Now, what we see is like usually this server part, this cache server or database. If we stick to the database server, it's usually managed by a separate team. And if it's managed by a separate team, we can even move one step further and put this cache in the cloud. So this cloud topology is kind of client server, but it's very specific because your server part is not managed inside your organization. So this is a diagram. It works the same as the client server. Your application uses cache client to connect to the cache server, but server is located in the cloud. It's located in the cloud. It means that you don't need to do all this management. You don't need ops team to manage this. You basically need to pay for the cloud provider, which is actually usually, as we know, the cloud, it's usually cheaper than doing this on your own. So how the client configuration would look like for that? This Spring, this is how the configuration looks like. So you create your cache server in the cloud using console or CLI, and then your cache server returns your discovery token. You put your discovery token in your client configuration, and again, client will find its way to the cache server located in the cloud. And by the way, this discovery token idea, it's not only about Hazelcast. Actually, most tools, I think Mongo, they do the same. They just, you create this, you create your server part using web console, get the token, put it in your client application, that's it. Short summary about client server and cloud solutions. So good sides. Your data is separated from the application. You have separate management. And it's programming language agnostic because you use cache client to connect to the cache server. From the downsides, you need to have some separate ops effort, or you need to pay for the cloud solution. Now, I mentioned here also higher latency. So it does not necessarily be higher, but you need to think about latency. So caching is like, the domain of caching is like very demanding in terms of latency. So we expect very low latency from caching. That is why if you deploy your server on premises, you better make sure that your cache server is deployed in the same local network where your application is running. Because even one router hop in between is a lot in this low latency domain. Now, if you use cloud solution, you need also to think about it. Because like if you use Hazelcast Cloud, we don't provide the infrastructure. We use underlying cloud provider like AWS, GCP, or Azure. And now, if you create your cluster, you should use the same cloud provider, underlying cloud provider, where your application is located. But that's not enough. You should use the same region where your application is running, because you don't want to, connect from Canada to Europe, because your latency would be crazy high. Now, but that's even not enough. We provide a way to do a VPC peering between your application network and network in which we created a caching cluster for you. So then you are technically in one virtual network. So there's no even one router hop in between. And that's something important, because otherwise your latency will suffer. The next pattern, Sidecar. So far, embedded, client server, these are all very old concepts. Sidecar is something new. It's very well known in Kubernetes, but it's not only in Kubernetes, but it's only in containerized environments. So what's the idea behind Sidecar, cache as a sidecar? So again, like request goes to our Kubernetes server service, it's load balanced to the one of the Kubernetes pod. And now in the Kubernetes pod, it's not only application container running, but there is also a sidecar container with the cache server. And now the application uses cache client to connect to the cache server, which is always located in the same pod because it's running as a sidecar. So application can use localhost to connect to the cache server. And now all these cache containers, all these cache servers from each Kubernetes pod, they form one consistent caching cluster. So you see, like, this idea is somehow, it's a little like embedded mode, a little like client server. It is like embedded because we know that our cache server and our application, they are running on the same physical machine, because that is guaranteed by Kubernetes that all containers in one pod, they are running in the same physical machine. So if you scale up, scale down, you do it together with your application. And there's no discovery needed. It's always localhost. But it's also similar to client server, because after all, you use cache client to connect to the cache server, so you can use any programming language you want. And there is some kind of isolation on the container level between your application and the caching server. How it looks like in practice. So the configuration, it's like a static configuration with localhost, but we know that in general, it only looks static from the application perspective, but in general, it's dynamic. We just know that the cache server is deployed as a sidecar container, which is available at localhost. And this is how your Kubernetes configuration will look like. So we have two containers. One is our application, so our custom business logic, and the second one is the cache server, and they always go together. Short summary, what is good about it? So we have simple configuration again. It's programming language agnostic. We have low latency, and there is some isolation of data. From the downsides, we again do not have flexible management over our caching cluster. And after all, the data is collocated in one application pod. The last pattern for today is cache as a reverse proxy, so reverse proxy caching. And reverse proxy caching is something completely different. It's something completely different from what we've seen so far. It's different because so far, the application was always aware that such a thing as a cache exists. Now we will put cache in front of the application, so application will not even know that there is such a thing as caching. So how are we gonna do it? So request goes to our system, and now just before the load balancer or just after, or together in Kubernetes service. In Kubernetes, you can even put it in your ingress, because ingress is implemented using Nginx. We put a reverse proxy caching. Nginx, by the way, is a very good solution for reverse proxy caching because it's very, very mature. And so you can use Nginx for this. And now, if request is found in the cache, it does not even go to the application. So application does not even know, okay, that there is such a thing as caching. Configuration for Nginx looks as follows. That's the simplest you can do. Obviously, you can configure more. So it's pretty straightforward. Nginx is very mature. This is ready to be used. Now, Nginx is great, but it also has some issues, like it's only for HTTP. Maybe it's not an issue, it's just a trait of Nginx. However, the issues are it's not distributed and it's not highly available. And also, data can be stored on disk. So Nginx does not necessarily store data on the disk, but it can offload the data, which is not, for example, the case for Hazelcast, when you are guaranteed that your data is stored in memory. So you are guaranteed about the low latency. Here, you need to think about it. So about reverse proxy, there is one variant of the reverse proxy caching, which is called reverse proxy sidecar caching. And this variant is becoming popular, and I personally think this will be the future of caching, like in Kubernetes and all these containerized environments. So how it looks like. So we combine the idea of sidecar and idea of reverse proxy caching, and that is the diagram we ended up with. Request goes to Kubernetes service. It's load balanced to one of the Kubernetes pods. And now inside the pod, it's not the application that receives the requests, but it's a reverse proxy cache container, which is kind of cache server, also like an interceptor of the network. And now, if the request is found in this reverse proxy cache container, it's just return the cached value. However, if the value is not found, only then it is passed to the application container. Now, all this idea that we put caching in front of the application, it is good and bad. It has good sides and bad sides. And let me elaborate on that. So firstly, what is good about it? Why I said I think is the future of caching in Kubernetes, and why I think it's good. You remember this diagram from the beginning of the presentation. So a lot of services, they use each other, generally written in different programming languages, generally a mess. Now you can look at the system, do some measurements, and you can decide, I would like to introduce caching to these two microservices. And now you can do it in a declarative manner. So you don't even need to touch the code of the services, but on the configuration layer, you can introduce caching to these two services and improve the performance. So that is the whole beauty of the reverse proxy caching. How it looks like in Kubernetes. So like this will be a sample configuration where you actually need 3 containers. One is init container. Let me explain why. So starting from the bottom, we have our application with our business logic. Then we have our caching proxy container, which is our cache server and also the interceptor of the network. But we also need an init networking to configure the network so that any request coming from outside does not go to the application, but it goes to the caching proxy. So this is our diagram, and it's this whole idea of declarative configuration. It may make you think about Istio service meshes, because that's the whole idea. I mean, on the declarative manner, you configure you change the behavior of your system. And actually, Istio recently re-implemented like the support for HTTP caching. So I think this will be the first widely used solution of the reverse proxy sidecar caching. So, and I really think it will be great, not only with Istio, but actually in every service mesh that uses Envoy proxy. But I also said, okay, it's not everything is so great about reverse proxy caching. And let me explain what is becoming more difficult with the reverse proxy caching. So actually, if you look anywhere on the internet, what is the biggest problem about caching? Everyone will tell you the same. That is the cache invalidation, meaning when to decide that you should no longer use cache value, but go directly to the source of truth. So that is the whole problem, that when the application is not aware of the caching. Because if the application is aware of the caching, then you can use some business logic to decide, okay, if something happens that I don't use cache, I go to the database, or I go directly to where the data lies. But with the reverse proxy caching, you cannot do it. You are basically bound to what HTTP offers, like timeouts, e-tags, basically timeouts. So that is the biggest problem with the reverse proxy caching. Short summary of the reverse proxy and reverse proxy sidecar caching. So the good thing about it, and the reason why you will use it, is it's configuration based. So no need to change your application. It's programming language agnostic, it's everything agnostic. And it is very consistent with the microservice world. From the downsides, you cannot do custom cache invalidation. There are no major solutions yet. I think Envoy proxy will change it, and it's protocol based. So that was the last caching pattern I wanted to present to you. So as a very short summary, what I thought it would be good as a summary, I would like to present, I will not repeat anything I said before, but I would like to present, to structure this knowledge somehow, a very simple, maybe oversimplified decision tree diagram of which cache is for you. So the first question I would ask is, does your application needs to be aware of caching? If no, are you an early adopter? If no, use reverse proxy. If yes, use reverse proxy sidecar caching. Now, if your application needs to be aware of the caching, then the next big question is, do I have a lot of data or some security restrictions? If no, then do I need to be language agnostic? If no, use embedded or embedded distributed caching. If yes, use sidecar. Now, if you have a lot of data, some security restrictions, basically you work in a big enterprise, then the last question you need to ask is my deployment a cloud? And if no, use on-premises client server. If yes, use a cloud solution. So you see, it's a little simplified, maybe oversimplified, but it at least gives you the direction where to look for. Now, as the last slide from this presentation, I would just like to mention a few resources. So the first link is the source code for all this caching pattern, where you can try them on your own, how they look like in practice. Second link is a blog post explaining how to set up Hazelcast as a sidecar container. Third one is a prototype of reverse proxy sidecar caching with Hazelcast, but it's on the prototype level, so nothing that you can really use on the production. And the last one is a very good video talk about Nginx as a reverse proxy caching. And with this last slide, I would like to thanks a lot for listening. It was a really pleasure to speak at this meetup.
Thanks, Rafal, for the great talk. I'll turn it over to Johan. Looks like we have maybe one question.
Okay, thanks very much, Rafal. Question over here. As a disadvantage of reverse proxy sidecar, I'd like to add that having to edit the network layer means everything will go through the reverse proxy sidecar? Or is there a way to say for these URLs, go to the sidecar, and for other URLs, just straight to the application? Sort of like application load balancing at the pod layer. Does that make sense?
Yes, I think it will depend. As I mentioned, it's very early thing, like in the implementation of this reverse proxy sidecar thing. But I think you need to have a way what is cached or not, what is not cached. I mean, it's not, you don't want every request going to the sidecar to be cached. So I think this will be this how it needs to be done.
Great. Well, thanks very much, Rafal. And one more quick question. This one from Romain. I would add another question in the last diagram. Does my application has lots of replicas in case of Sidecar's caching solutions? So if the service has 200 pods, caching one key will take 200 times longer than having a single cache backend. What do you think would be the case in that situation?
Not really, because caching, does not work this way. If you have like a caching cluster, it does not store. You have let's say this 100 nodes of cache server. No matter if it's Sidecar or you just have 100 nodes of your caching server, and they form one cluster. Now you don't store 100 copies of the same data. It's obviously it's configurable, but usually at least default, what we do is you store just one backup. So it means that you store your cache. It's partitioned over your caching cluster. So it means that I write to one node, one cache node, cache server node, and then it's backup to one of them. But you can configure this, but you will almost never configure this to be for the backup to be on every other node, because that would be slow.
Okay, awesome. Thanks very much, Rafal.
All right. So thank you, Rafal. If there are more questions, please feel to leave in Q&A. I think, Rafal, you'll be in the chat.
Sure.
And just to continue, that we do have a survey for these talks, so keep it open. We do have some swag planned, but to make mindful of time, let's introduce our next speaker.
Yeah, our next speaker is Pete Saia. He is a senior software engineer at the New York Times, and he is focusing on building scalable and secure authentication and authorization systems. His talk will be about Knative tooling and observability at the New York Times. Pete, take it away.
Hello, everybody. Let me just try to share my screen here. So first of all, hello. I am Pete Saia, and I am a software engineer at the New York Times. First, I just want to take a moment and thank Sebastian for the invite. It is a pleasure to be here. I'm located currently in Brooklyn, New York, and I'm going to be talking about the next generation of infrastructure that our team services will be built on top of. I'm just going to be scraping the surface of a lot of big topics in a short amount of time, so forgive me if I speak fast. I also want to note that the solutions that I'm going to be going over today are still in flight. This is mainly work that we've started really just at the beginning of the year. And that said, I am still very happy with where it's going, and it's showing a lot of potential for scale from both a performance and an organizational adoption standpoint. So before I get started, I'll just go over the agenda as a little historical context, just showing where we are and where we're going. I'll be talking about dark deployments, cloud agnostic identity and zero trust networking, the build process and development, local development, and finally, serverless observability. So first, I just want to lay some context on the type of infrastructure that our team inherited. It's a bit of a charcuterie board of cloud vendor products. And I think it illustrates the difference between being multi-cloud and stuck in multiple clouds. And these products, primarily on the GCP side, illuminated a few clear problems, which resulted in requirements and a checklist for the new infrastructure. We can see we're both in AWS currently using Oracle and EC2. And within GCP, we're mainly using GAE, Cloud Functions, Memory Store, along with a few others. And the requirements for the new world are an excellent local development environment. And this was really, we were burnt by some of the products in GCP of just offering a pretty poor local development environment. And it just results in slow development cycles. Access to low-level primitives. This is kind of the same story. Not everybody on the team or in the company has deep Kubernetes experience. So I wanted to make sure that just deploying a service doesn't require more than one file. Simple preview environments, and we'll get into that shortly. It should be multi-region and multi-cloud capable. And finally, for observability, we're doubling down on Sumo Logic and Datadog. And everything should be GitOpsable. So the stack we landed on, the TLDR, is starting from the bottom up. It's Kubernetes with Istio on top of Knative, and then Cert Manager, a Datadog agent, and Vault. And this is, again, is a very high-level stack, and the rest of the slides will be talking about the nuts and bolts and how these work together to accomplish our needs. So I'll start with this concept or notion of deploying dark and how Knative revision solves that problem for us. So a typical development cycle on our team looks a little something like this, at least for the public products. We'll create a PR, and from that PR, a preview environment will be spun up. And the developer can share this preview environment with various stakeholders. They can take a look at it, review it. You can make changes, commit to that preview environment, and ultimately it will be merged back into the main branch and deployed. We're currently doing this with GAE, and it's more or less hacking GAE to make it work, but it does work. And we wanted to make sure that this new infrastructure can do the same thing. We certainly don't want to lose this feature, but we also don't want to have to rebuild something from scratch, which is really where Knative revisions came to the rescue. And looking a little bit about how this works is by creating a branch or using the branches, the Git branches as tags, we're able to actually specify which branch we want to be serving 100% of the traffic and deploy revisions to that branch. And since we can define how much traffic each branch gets, we can actually deploy the PR branches with 0% traffic and use those as our dark deployments. And looking in the pipeline, how this looks is on a regular deployment, this task looks fairly simple. We just specify the project name in GCP, the region, the cluster name, and it will deploy it with 100% of the traffic. For a dark deployment, we simply need to pass in the dynamic branch name. We're using drone, so the environmental variable is drone branch. By doing this, that drone branch instance will be deployed except with 0% traffic. And I'll get a little bit into the mechanics of how that's done. And just, I'll note that this is done using the KN CLI tool, which is a Go tool, which is used to really just abstract. It just makes working with Knative services a little bit easier. So as I mentioned, a regular deployment looks a little something like this. First, we'll deploy and remove all of revisions serving greater than 0% of traffic. And then we'll add that revision at 100%. It's fairly simple. That's all it takes to get something live. For dark deployment, we reapply the entire state of the world with the new revision included at 0% traffic. And what that looks like, and this is really just a series of KN CLI tool, excuse me, this is just a series of KN commands in a fancy bash script plugin, which you can see in this first step, we gather the state of the world. This is really just obtaining all of the current revisions in their traffic, which then allows us to, depending on if it's a dark deployment or a regular deployment, decide if we want to deploy at 100% traffic or 0% traffic, and then ultimately we apply those tags accordingly. So really without much tooling at all, we're capable of getting this concept of dark deployments. Next, I'm going to be talking about cloud agnostic identity and zero trust networking. First, what is identity? Identity is something that belongs to each service. It's cryptographically verifiable. In our case, we're using 509 certificates. And it includes a SAN, a subject alternative name, which has a SPIFFE URI, which contains the trust domain and workload identifier. And if you're not familiar, SPIFFEs are I believe a CNCF incubator project, and are used for this very purpose of applying identity to the workload. And you can see here, the convention we're using is we're applying the team as a preface to the domain. Finally, after the slash, we provide the workload identifier. In this case, it's service foo. And that TTL is 15 minutes. And I'll get into that a little bit on the next slide, but it's purposely very short. Next is, what is zero trust networking and how to accomplish zero trust? So the basics are, it means there's zero passwords to be compromised. And we finally assume that the network is not safe by default. So the secret sauce to this has been Vault, which is already widespread adopted at the times. And we were able to lean on it quite heavily to accomplish this. Simply by using the metadata API, which Vault does in the background, on an instance that's deployed, we can, it essentially pings the metadata API for the app role and then gets assigned JWT and uses that to authenticate with Vault. So we can effectively authenticate with Vault without a password, which is the first and key step to this whole process. Next, when we put it all together, when we put it all together, we can do something quite powerful. And below shows kind of two clusters in a diagram where, and how they may speak to each other. I think, you know, it's fairly understood by now how two services in the same cluster speak, especially in Istio environment with MTLS. This is very much the same thing, except they're outside of their clusters. So below we can see a sample MTLS request from cluster A to cluster B. Specifically, service foo is pinging service bar, And we can see that we're using HTTP as the URL in cluster A. And it's purposely HTTP and not HTTPS because we're leveraging Istio's egress gateway to perform TLS origination, which applies the certificate to the request automatically, which allows that service foo pod to be certificate agnostic and really not have to worry about that TLS at all, which makes building these applications a lot simpler. And similarly, in cluster B and in service bar, when it receives that request, it is also agnostic of the TLS, as that TLS is terminated with an envoy. And also, there's an envoy filter, which is applying some RBAC filter logic, which I'll get into on the next slide. But more importantly here, it keeps the pods within these two clusters agnostic of any type of authorization or authentication to each other. That logic is at a higher level. And the final note here is Cert Manager is the thing running in each cluster that is keeping these certificates refreshed every 15 minutes, or it could be every 5 minutes. But the important thing here is that the TTL is short, because the number one thing, or at least top three thing that keeps us safe is a short-lived TTL. And I just want to zoom in a little bit on that last step on that envoy filter. And we use a Git-based kind of self-serve model that allows teams to come and decide what they want access to. And the envoy filter itself is a little bit of a gnarly YAML file, as it can be. It's quite deep, and there's a lot going on. So we created a customized generator that abstracts that filter and creates a very simple interface, fairly simple interface for others to go in and decide what role they want access to and put their spiffy as a principal on that role and decide which roles they want to have access to. And then we can come in and review the PR and finally decide to merge it, and it will update the filter accordingly. Next, I'm going to talk about the build process and how we decided to do local development. So first and foremost, we built a command line tool to handle this. And we wanted the way that we deploy locally to be the exact same way that we deploy remotely. And this allows for, first, much more resource efficient development, and also a much faster development cycle and feedback cycle for testing things. And this even includes testing things like observability logic or service-to-service communication. It may not always be necessary to deploy the entire world every time you want to work on a service, but it's definitely nice to have when you want to do something that is cluster specific. And what that pipeline looks like is, in the first step, we configure either kind, GKE, or EKS, and we are leveraging kind for local deployment or for local development. Next step is applying the Terraform. This really provisions the cluster if it's remote and configures any IAM image pool secrets. And an important step here is we actually output the Terraform outputs are saved as variables. And you'll see those variables actually get applied to the customize at a later step. So things like if we, provision an IP address or static IP address or a Redis instance, we want those dynamic IP addresses to be used in the Istio YAML files sometimes, and Customize doesn't offer really templating. So we can we save these as variables, and those will get passed in dynamically to Customize. Next, we provision Istio CTL. this ultimately, or rather this ideally would be done all fully in customized, but Istio is a bit rigid when it comes to its install still. So we do this as a first step just to keep things clean. And then finally, we apply the customize. This includes all the inflators and generators, applies the bases, and finally applies the overlays. And I just want to zoom in a bit on this customize step. Now, at the organization, there's still a fair amount of Helm usage. This includes for external projects and internal projects. And it's a bit hard to just say, all right, everybody, we're not going to use Helm anymore. We're just fully betting on customize. So we need to convert all of these Helm charts to customized bases. And while that's maybe a good thing to do, it's not a practical thing to do right now. So we're actually able to work with Helm quite elegantly using something called inflation. So we can see in the manifest stream of a customized stream, we inject the Helm chart as a first step, and then finally we can apply our overlays to that Helm chart if we want to. And I'll zoom a little bit more into that process here. An example for the Sumo logic inflator. We can see on the left, there's a customized plugin. This is really just a bash script that outputs to std out. And we use Helm template to do that. And we can create as many configurations as we want to that actual Helm build and pass through the ultimate customized YAML on the right. But more importantly, it allows us to continue to use the maintained Helm chart as we would, and also apply any overlays to it later on. Next is, I just want to discuss how we are federating our projects. We have a single repository for the specific repo or the specific cluster, and repositories for every single service that belong to that cluster. And we can see the service-specific CI pipeline on the left. This is for, say, a service foo, where it wants to deploy to both cluster foo and cluster bar. It can do that simply by creating steps in that CI pipeline that tell it to which cluster to deploy in. Finally, serverless observability. As we know, Knative is known for dealing with these ephemeral, quickly growing and shrinking pods. And it's hard to do the pool model of Prometheus pool on these. So we have adopted the Prometheus push gateway. So instead of pulling, we're pushing our metrics to a push gateway service, which offers an endpoint for a Datadog agent to then come and scrape using the Open Metrics scraping plugin. So in this diagram, you can see we're both scraping our Prometheus push gateway and the Istio metrics in the exact same way, and not actually using Prometheus itself for aggregating the data. And that's really it. Finally, I just want to mention that we are hiring at the Times. If you think this is interesting and you like working on this type of thing, check out our open positions. This is actually a link. Feel free to check out the deck and check them out. We would love to hear from you. And open for Q&A. Am I doing on time?
I think you're doing okay. That was a great talk.
Thanks.
Any questions in the Q&A, Johan?
We just got one. So is the spiffy name set a tag in Prometheus push gateway?
It is. And I should have included actual observability dashboards from this. But it's a really great thing to have because we can see exactly where the traffic's coming from using the Spiffy, which is actually a feature that we didn't actually anticipate until we started configuring these dashboards, and turned out to be really great.
Yeah, I can imagine those spiffy tags being a really nice way to see it, and the cardinality is not too much if you're dealing with things like Prometheus.
Any other questions? Feel free to add them to the chat, and we will make sure you get in touch with Pete. Thanks very much, Pete.
John, I have a very quick question for Pete. Do you have any other example of the Helm plugins you use, or how you use the Helm plugins to extend to render other charts or other stuff?
I do. So I don't have any examples in the deck or on hand, but currently we're using a plugin for converting using environment substring, the env subst, that actually takes those variables, those outputs from Terraform, and injects them into Kustomize. And this gives us a little bit of the best of both worlds from Helm and Kustomize by allowing us to transform the two environments. That said, we're being very cautious and careful about what we decide to import to make sure we don't go crazy. And we're really just leaving those variables as being things like IP addresses, and really just IP addresses. Anything that we definitely can't check in will be injected. Finally, we're also using it for the Datadog chart. Datadog is still really just maintaining their Helm chart as the preferred way of installation, specifically for the Datadog agent. And that is a pretty gnarly looking chart. So I decided not to take a screenshot of that, but that would be the third plugin. I think that's it. And actually, and of course, the RBAC plugin, which I showed, and that actually abstracts the Envoy filter, it would be the final plugin.
Thanks a lot.
Sure.
Awesome. Thanks, Pete. I would love to see like a blog or something like that, or even a GitHub post for all those sort of plugins. But a question from Roy here. I miss OPA in the zero trust architecture. Any comments on why you did or didn't choose to go with OPA, or did you and you just didn't put it in the slides, or?
No comments. I guess I'm not the, I'll have to look more into that, like the open policy agent. Yeah, no comments so far.
One last question from Brad. Did you examine alternatives to Kustomize, such as Carvel's YTT? I don't know Carvel's YTT offhand. I'm not sure if you do, but any alternatives that you investigated?
Well, we started out actually with Helm, and that, it's kind of a long story, but yeah, we started out with Helm. I'm not familiar with the tool that was named the YTT. I'll check that out. But no, it was really just Helm versus Kustomize.
Well, thank you very much. Thanks for your time, Pete. I appreciate it. And it looks like Sebastian's posted a URL for the Carvel tool in the chat here, so you can take a look at that after me too.
All right. So just to wrap things up, remember we are collecting a survey. I'll post the link again if I can find where my link went. Let's see, share screen. Let me share my screen. Try this one more time. screen. So we are collecting surveys for these talks, whether you liked them, feedback. It's our sort of little post-event survey. We have some swag to give away. We have a cap, some Cube socks, Cube mask. So yeah, please submit the survey. All your feedback is really, really welcome, both for our speakers and our event organizers. We'll collect these results and be in contact. If you are a winner, we'll have given away swag. So please fill out these surveys. And as always, a big thank you, big merci from the CNCF Cube Eastern Canada Meetup team. We love hosting these events. We are starting already to think about what's in the next event, so stay tuned. And with that, thank you for attending today. We appreciate having you and hope to see you next time. Take care, everyone. The recording will be available. We'll share it out. In case you joined late, we'll send it out.